So hello everyone, welcome to this series of video lectures in which I am discussing about the Dirac delta functions. In the previous lectures we saw how to define a Dirac delta function and how to represent a Dirac delta function or how to model a Dirac delta function as a limiting case of other functions, and we also saw that the exponential representation of the Dirac delta function. Now in this video I am going to discuss about its properties. So the first property is integration from minus infinity to plus infinity delta x dx is equals to 1. We already saw it in that it is the definition of the Dirac delta function. So now the second one is f of x delta x minus a is equals to f of a delta x minus a. So to prove it, let's consider any arbitrary function f of x. This is f of x. Okay, now let's consider a delta function defined at x equals to 0. Okay, say in general let's consider it is defined at x equals to a. Okay, so now let's consider 3 points on the x-axis. So this is the this is delta x and these are the x-axis. Now let's consider 3 points, say x equals to, say, this is b and this is c. So 1 point, say x equals to b is less than a, and another point is x equals to c is greater than a. So for these values x equals to b and x equals to c, the value of this delta function is always 0. So if you multiply delta x with fx, you will always get 0. So there will be no value. But for x equals to a, you will find that there will be a peak, and you can define, if you multiply delta x with fx, its value will not be 0. So you can say that you will get only the value for fx at the point where the delta function is defined, or where the value of the delta function is not 0. So from this argument we can say that f of x delta x minus a is equals to f of a delta x minus a. So that is where this delta function is defined. So now the next property is, if you integrate it over the region minus infinity to plus infinity, f of x delta x minus a dx, it will give f of a. It is really easy to prove because f of a is a constant, and you will be left with integration minus infinity to plus infinity delta x minus a dx, and we also know from its definition that this integration is equals to 1. So we will left with f of a. Okay, so basically I integrate this term from minus infinity to plus infinity. So another way of writing this is integration from a to b f of x delta x minus c dx equals to f of c if c belongs to a and b, and it will be 0 if c doesn't belongs to between a and b. Okay, so this is another way of representing this property. So our next property is x times delta x is equals to 0. There are various ways to prove this property, but let's consider this property. So f of x delta x minus a is equals to f of a delta x minus a. But in our case, fx is x, and this delta function is defined at x equals to 0. So x time delta x minus 0 will be, you have to put this 0 in the argument of fx, and it is x in this case, so it is 0 times delta x, which is 0. So this is how you can prove, and there are lots of various other ways to prove this also. Now next property is integration minus infinity to plus infinity delta a minus x delta x minus b dx is equals to delta a minus b. Okay, so to prove this property, let x minus b equals to y. Therefore x will be equals to y plus b, and dx will be dy. So our integration becomes minus infinity to plus infinity delta x minus a minus x delta x minus b dx is equals to, the limit will remain same, minus infinity to plus infinity. Now the argument of this delta function becomes a minus y minus b. That is, I am putting this x equals to y plus b in this place of a minus x. Okay, and the second argument will be delta y dy. So it is equals to minus infinity to plus infinity delta a minus b minus y delta y dy. Okay, but this delta function is defined at delta y minus 0. So again, if you consider this delta function as another function, say f of y, then you have to put this 0 in its argument, so it becomes delta a minus b. Okay, again another way of representing this property is integration minus L to plus L delta a minus x delta x minus b is dx is equals to delta a minus b if a greater than minus L and b greater less than L and 0 otherwise. Okay, so our next properties, which is number 7, delta k minus x is equals to 1 over mod k delta x. Okay, so to prove this property, let's consider this integration from minus infinity to plus infinity f of x delta k minus x dx. Now in case 1, let's consider k as a positive quantity. K is positive, so let kx is equals to y. Therefore x equals to y by k, and dx is equals to 1 over k dy. Okay, so our integration becomes minus infinity to plus infinity. The limit will remain same. F of, now x will be replaced with y by k delta, and in place of kx we will write y. So and dx will be replaced with 1 over k dy. So this is equals to 1 over k integration from minus infinity to plus infinity f of y by k delta y dy. Again, this delta function is defined at y equals to 0. So and this is a function of y. So again, using the previous property of the delta function, you have to put this 0 in place of y, and you will get 1 over k f of 0. So we have, therefore what we have is that minus infinity to plus infinity f of x delta kx dx is 1 over k f of 0. Again, you can represent this f of 0 as 1 over k minus infinity to plus infinity f of x delta x dx. So by equating this one and this one, you can say that delta kx is equals to 1 over k delta x. So we prove this by considering k as a positive quantity. Now let's consider k as a negative quantity. So case 2, k is negative quantity. So again, if you consider this k as negative quantity, and if you let minus kx equals to y, then you can show that again this integration minus infinity to plus infinity f of x delta k of x dx will be equals to 1 over k integration from minus infinity to plus infinity f of x delta x dx. So again, from this case, you can argue that delta kx is equals to 1 over k delta x. Take it as a homework problem, and let's try it on your own. So in general, you can say that so we get the same expression for both positive and negative k. So in general, you can say that delta kx is equals to 1 over mod k delta x. Okay. So our next property is delta of minus x is delta x. That is, delta function is an even function. Okay. Now to prove this property, let's take help of this one of this relation, that is delta kx equals to 1 over k delta x. Now in this case, let's write it this delta of minus x as delta of minus 1 times x. So in this case, this k is equals to minus 1, and from this relation, above relation, we can write it 1 over mod of minus 1 delta x, and 1 over this mod of minus 1 is equals to 1, so we can say that delta of minus x is x. Okay. So our next property is derivative of the delta function, or derivative of delta of minus x is equals to minus of delta derivative of delta x. So we know that delta of minus x is delta of x is equals to delta of x. That is the even property, that is the delta function is a even function. So now if you take the derivative with respect to x on both sides, then ddx delta of minus x will be equals to ddx of delta x. Therefore minus of delta prime minus x is delta prime x, or delta prime minus x is equals to minus of delta prime x. So this proves our property. Now the next one is delta kx plus minus b is equals to 1 over mod k delta x plus minus b by k. Okay. So this is really simple to prove, so you can do it on your own. So our next property is the derivative of the delta function. So this property is integration minus infinity to plus infinity f of x derivative of the delta function, that is the nth order derivative of the delta function delta x minus a dx is equals to minus 1 to the power n, and the nth derivative of the function f at x equals to a. So this is really a very important property. So to prove it, let's consider this integration minus infinity to plus infinity f of x. Okay, let's consider, say, for n equals to 1, that is for first order derivative. So integration minus infinity to plus infinity f of x, and for first order dx of delta x minus a dx, which is equals to, now we are going to integrate it by parts. So f of x, now integrate ddx of delta x minus a, and it will give delta x minus a, and the limit minus infinity to plus infinity, and minus integration minus infinity to plus infinity. Now you have to take the derivative of this function f of x with respect to x, and you have to integrate the delta function x minus a dx. Now this first term will take the value 0, because this delta function is defined at x equals to a, and it is 0 otherwise. So if you put plus minus infinity, that is for any other value of for any other values of x, it will be 0. So this multiplication will also be 0. Okay, so we are left with this one, minus infinity to plus infinity f prime x delta x minus a dx. Okay, now if you consider this derivative as another function gx, and if you use the previous property of the delta function, that is integration from minus infinity to plus infinity fx delta x minus a dx is equals to f of a, then you will get it is equals to minus of f of prime a, or you can say that minus 1 to the power 1 f of prime a. Okay, so if you take if you consider the value for n equals to 2, that is the second order derivative, then you will get minus 1 to the power 2 f double prime a, and so on for the increasing value of n. So in general you can say that this relation holds true. Okay, so this is a general expression for nth order derivative. Now let's consider our next property, which is x delta prime x equals to minus delta x. Okay, so it is again really simple to prove. Let's consider this integration minus infinity to plus infinity x delta prime x dx, and again if you integrate it by parts, then you will have x times delta x minus infinity to plus infinity minus infinity to plus infinity. Now you have to differentiate x with respect to x, which will give you 1 times delta x dx. So it is minus infinity to plus infinity delta x dx. So by equating this one and this one, you can say that x times delta prime x is equals to minus of delta x, and this proves our property. Now the last and most important one, Dirac delta function of function. Okay, so this property tells us that delta of a function, say gx, is equals to sum over I is equals to 1 to n delta x minus xi by mod of g prime xi, where xi's are the roots of the equation gx equals to 0 and g prime x is the first order derivative of g of x. Okay, so now let's consider this delta function, delta of x square minus s square. So now you can't write it in directly to any of the following any of the property. So now to evaluate it, let's consider this argument x square minus s square as another function gx. So gx is equals to x square minus s square. Now let's find its roots. So gx equals to 0 and we will have x equals to plus minus a. Now its derivative will be g prime x equals to 2x. Okay, so what do we have according to this relation? Delta x square minus s square is equals to, now we have a sum over, so let's put the first root, which is x is equals to plus a, so x minus a by mod of g prime xi, so xi is the root plus a, so it is 2a. Again plus this plus sign is due to this summation, so delta x plus, that is x minus of minus a, which is x of plus a, divided by minus 2a. Okay, so what do we have is delta x square minus a square is equals to 1 over mod of 2a times delta x minus a plus delta x plus a. So you can consider it as another property, say 14. Okay, now consider another function, delta of x minus a times x minus b. Okay, so to find its root, that is, let's consider gx is equals to x minus a times x minus b and equate it with 0. So gx equals to 0 will give you the roots. So we have x equals to a and b are these are the two roots. Okay, now g prime x will be equals to d dx of this expression x minus a x minus b, and it will be x minus a plus of x minus b, that is the derivative of the first one, keeping the second one outside the derivative, and also for the second case. So it is 2x minus a plus b. Now let's use the above relation, this one. So using this relation we will have delta x minus a x minus b is equals to sum over I equals to 1 to n. Okay, let's write it directly. So delta x minus a mod of a minus b, that is mod of g prime at x equals to a, which is a minus b, plus delta x minus b mod of minus of a minus b. Okay, so you will have delta x minus a x minus b is equals to 1 over mod of a minus b delta x minus a delta x minus b. Okay, so again you may consider it as another property of the delta function. Let's number it with 15. So these are the properties of the delta function. Okay, so see you in the next video, and in the next video we will find the Fourier transform and the Laplace transform of the Dirac delta function.